The reaction today is the synthesis of an alkyl bromide from an alcohol using nucleophilic substitution. So we will be starting with an alcohol, not specifically cyclohexanol, but I will use this as a representative sample. We will be adding some acid to this, which will protonate the OH, converting it to a better leaving group. Now, this should look fairly familiar. Last experiment, we did the same process using phosphoric acid, but in the process we synthesized an alkene. We had an elimination reaction. We lost the water, regenerated the acid catalyst, and made an alkene. This time, we will be following the same procedure initially, adding some acid, but now we will have some bromide anion present from sodium bromide. The bromide anion is a nucleophile, and so it can substitute, attacking that carbon, kicking out the oxygen, and instead of an elimination, we get a substitution reaction. In this case, we're getting a substitution rather than an elimination reaction because we have a good nucleophile present. In the last experiment, the only nucleophile we had present was the conjugate base of the phosphoric acid. Remember, phosphoric acid is H3PO4, and this can dissociate to the H+, our hydrogen ion, and it leaves us the conjugate base of H2PO4, the hydrogen phosphate anion, and this is a poor nucleophile. Indeed, for this reaction, we're using sulfuric acid. Again, the conjugate base that we get after the hydrogen ionizes is the hydrogen sulfate anion. This as well is a poor nucleophile, so if all we did was add sulfuric acid, this would also follow the path of elimination. But in this case, we're getting a substitution reaction instead. The procedure that we're going to follow, initially we're going to combine all of our reactants except the sulfuric acid. So we will combine our sodium bromide, we're going to be using water as a solvent to dissolve that, and the alcohol, and these will be combined in a round bottom flask. We will then set up for reflux, and then we add the sulfuric acid through the condenser. The reason we do this is twofold. First, we are using concentrated or 18 molar sulfuric acid. And the acid has a high heat of dilution, meaning that when we add the sulfuric acid to our reaction mixture, the mixture is going to get fairly hot. If we simply poured it in, there would be the risk that we might heat and get some boiling, at least localized boiling, and have some of the acid splash out. And we want to minimize the risk of that. By having it reflux condenser on there, there's no likelihood, even if it does start having some localized boiling, there's no likelihood it will splash out and get on your skin. Also, specifically why we use 18 molar, or the concentrated sulfuric, is that the one of the products of the reaction, you'll notice up here a byproduct is water. And so if we add water, since this is an equilibrium, if we remember Le Chatelier, remember his principle that if we add more products, we will push the equilibrium back to more reactants. And so the more water we have present, the more likely we are to be pushing that equilibrium to reactants, meaning we get less product. So if we used a more dilute solution of sulfuric acid, we would hinder the reaction from going to completion. And so we want to minimize the amount of water, and so we use concentrated sulfuric acid. Once the sulfuric acid is added, at that point we heat the solution at reflux. And we do this for two reasons. First, we'll address specifically why we heat. Heat accelerates the reaction. So by heating, we make the reaction go faster. This reaction would proceed at room temperature, but it would take much longer for the reaction to complete. By heating it, we can have it done in half an hour as opposed to several hours. Specifically, we heat using reflux to prevent evaporation or loss of our reactants, products, or solvent, any of the volatiles. Usually this refers simply to the solvent, which is our main volatile species. However, in this case, the alcohol that we are using is somewhat volatile, and definitely the alkyl bromides are fairly volatile. And so we use reflux to prevent that. Any vapors that do form will be condensed by the condenser back into a liquid, and it drips back into the flask. Of course, anytime you're doing a reaction, the first step is going to be the design of the reaction, planning the protocols, design and planning. Once that is done, and we've done that for you, the next step is to actually execute the reaction. So at the end of the reflux, we will have done that, but then we always have to separate and purify our product. When the reaction is done, we will have a mixture of any unreacted starting materials, solvents, catalysts, plus the product and possibly byproducts, and so we do need to separate that. And a final step, of course, is the characterization. We don't just assume that we made our target molecule. We have to show that by analyzing it, by characterizing it. So at the end of the reflux, we have finished the reaction step. We then have to go to the separation and purify. And so the next step is to distill the mixture, or specifically to distill our product. So at that point, we will simply take the reflux condenser off, convert our reflux apparatus to a distillation apparatus. Of course, before we do that, we will remove our flask from the heat and allow it to cool just enough to stop boiling. We don't need to get it to room temperature since we will be heating it again, but we do want it to stop boiling so we don't lose our products during the transformation. Then we simply attach a still head, the thermometer, and reattach our condenser, and then we distill the product. Of course, with the alkyl halides, since they are volatile, we do need to take care not to distill too rapidly to ensure that the vapors do have time to condense while they are in the condenser. One thing you will note when you do the experiment is that we do not simply get bromoalkane distilling. You will notice that there will be two layers. This is because we will be getting the bromoalkane as well as water. This is similar to what you observed in the previous experiment, the dehydration. In that case, the cyclohexene you were making and the water byproduct, they are not miscible. They do not mix with each other. And anytime you distill an immiscible mixture, you will get both liquids co-distilling. And we will see that again. The bromoalkanes and water are not miscible. They don't mix. And so when you distill, you will be receiving both, and you will see that in the collection vessel. It is also possible when you are distilling the product that since we are doing a simple distillation, the boiling points of the bromoalkane and the alcohol are not very different, and so we will possibly co-distill some of the alcohol if we still have unreacted alcohol. And so we will need to purify that. So to do that, we will be washing the solution initially. So we're expecting possibly, if we have some unreacted alcohol, that may co-distill. Of course, our main product will be the alkyl bromide, and we will also have water present. And so we will wash this solution, and of course when you wash, you're putting it in a separatory funnel. You mix, swirl gently, vent the separatory funnel as you do this, and then you separate the layers. You will have two layers. One is the aqueous or water layer, and this will consist of the water. The other is what we refer to as the organic layer, and this will contain both alcohol and the alkyl halide. We need to separate those. We can do that using 9 molar sulfuric acid. And again, we're going to have an organic layer. This is the alkyl bromide itself. And we will again have the aqueous or water layer. Remember, sulfuric acid is in water. And that will have the alcohol in it. Our alcohols are soluble in 9 molar sulfuric acid. The alkyl bromide is not, so we use that to separate the two. You will notice that we have 9 molar in this step. We also had 18 molar. So when conducting the experiment, you do need to take care that you do use the correct sulfuric acid. Now, it is possible when we're doing this, if you're not very careful with the separation, that you could have a small amount of sulfuric acid as an impurity in this layer. We do want to make sure we eliminate all of that, and so we will do a final wash. This final wash will be done with a saturated solution of sodium bicarbonate. Sodium bicarbonate is a base, so it will react with any residual acid. If you have a small amount present, it will react with that. And so the aqueous layer, the water, again the sodium bicarbonate is dissolved in water, will contain the sulfuric acid. Although at this point technically it's not sulfuric acid, since we will have had a reaction, it will be sodium sulfate as our product that's in the aqueous layer. But again, we're discarding this. One caution when you're doing this reaction, or this particular washing step, is that the sodium sulfate, the sulfuric acid, and the sodium bicarbonate will react. Of course, as I've mentioned, you get sodium sulfate as a product for this, but we also get carbon dioxide, and this is a gas. So when you are doing this reaction, you want to make sure you vent your separatory funnel immediately after adding the sodium bicarbonate. Otherwise, after the reaction, since we are producing a gas, we can build up pressure. We do have one other product here, water, just to complete that. But because of that production of a gas, we do need to take care to vent the solution so we don't build up pressure in the separatory funnel, which could potentially blow out the stopper that we use in the separatory funnel. And if it happens when it's inverted, then of course you're also going to lose your product, and we want to avoid that. Then final step is that we will need to dry. Again, when we're doing our separations, we may have a tiny amount of water mixed in with our AlkylBromide, so we do want to dry the bromoalkane. And you've done this before. The way you dry a liquid is to use an anhydrous salt, a drying agent. And we have several in the lab to choose from. We have anhydrous sodium sulfate, calcium chloride, and magnesium sulfate. But you do need to dry the solution, and at that point you can decant if you used sodium sulfate, or filter if you used one of the other drying agents, to isolate your purified and dried bromoalkane. And then, of course, the final step that we have is the analysis of the product. Again, we want to determine what we have. There are several things we can do. One, you can do a simple distillation of at least a portion of the product. Don't need to distill the entire amount, since all we're trying to do is obtain boiling point. Since the boiling point is characteristic of the alkyl halide that you have, we can use that to identify that alkyl halide. Another technique is infrared spectroscopy, or IR spectroscopy. In this case, we look not only at what is present in the infrared spectrum, but also we should look at what is absent. Remember, infrared spectroscopy tells us something about the types of bonds that we have. For an alkyl halide, the main thing we expect would be carbon-hydrogen bonds. But that was also present in our starting material. In fact, it's present in most organic compounds. And so seeing specifically sp3 hybridized carbon-hydrogen bonds is not going to be very instructive as to whether or not we made our compound. The carbon-bromine stretching frequency tends to be in the fingerprint region, so it's easy to confuse that with other peaks or not observe it. So with IR spectroscopy, we also look at what is absent. In particular, consider the starting material. We started with an alcohol, and so we can look to see if we see an oxygen-hydrogen stretching frequency. If we see that, typically out around 3400 wave numbers, that means we still have alcohol. If it is absent, it does mean that we no longer have our starting material. Of course, as I mentioned at the beginning, one of the routes this reaction could take, indeed that it took in the last experiment, is an elimination. So you could also look to see if you have sp2 hybridized carbon-hydrogen bond, or the carbon-carbon double bond. And when you are writing your report, you can specifically address these three peaks. Are they present? And of course, when you do that, you should state the region you expected, and then note the fact that these bonds are not present, indicating, number one, we do not have alcohol anymore, and number two, we did not have an elimination reaction, which would suggest that we probably did get the substitution reaction. And the full method of analysis is GC, or gas chromatography. And for that analysis, we look at retention time of the product that you produced. And of course, that alone does not tell us anything. We do have to compare the retention time to that of the standards. So if your retention time matches the retention time of, say, bromobutane, that would suggest that your product is bromobutane. And one final method for analysis is the NMR spectroscopy. And there will be a separate video to talk about the interpretation of the NMR spectrum. This will be very similar to what you did for the ester hydrolysis when you identified your alcohol. In that case, you used NMR spectroscopy to identify an alcohol. The interpretation is very similar. You won't have the OH peak, of course, and the hydrogen adjacent to the bromine will be in a similar region to that of the hydrogen adjacent to the oxygen in the alcohols. But we will discuss that, as I said, in a another video.